Okay. So as we discussed for this whole scheduling thing last time, so the next section I'm going to cover, starting now, Lagrange multipliers, also known as strained optimization. There's also 1.9 in the notes. Okay, so I have today and Monday set aside for this section. It may not take that long, the 2 full class periods to do this. So whatever time I have left over, like maybe some of Monday, as soon as I finish this section, whenever it is, I'm just going to start reviewing for the test. And then we'll serve and that time can also be used for homework questions. And so certainly all of Wednesday will be for that. Practice test is up. If you haven't looked at it yet, you should, since you have a week. Okay. Now, the problem we were looking at last time is to find a maximum or a minimum of some function f of however many variables you have. So n independent variables. Now, so now we know how to do that. We take the gradient, so all first partial derivatives, we set them all equal to 0, and then classify as a maximum from there. But this time we're going to add something to this problem, call it a constraint. So we're going to have one or more constraints on these independent variables. So the constraints are just equations. So we have some functions like g1 of the same variables must be equal to 0. G2, and so forth. Okay. So we have m total equations that give us constraints. So the procedure we saw last time of taking a gradient, setting it equal to 0, no longer applies because whatever critical points you get from this might not, or almost certainly will not satisfy these constraints, so you can't consider it. Now, constrained optimization in general, by the way, for terminology, this function we're trying to maximize or minimize is commonly referred to as the objective function. This is your objective to find where it's a maximum minimum. So this field of optimization is an extremely important field of real applications, like, certainly in business, for example, because you're trying to maximize something, profit, subject to a variety of constraints, like constraints on the resources you have. For instance, amount of space you have for production, for facilities, or time constraints, things like that. So all these things have to be taken into account, and we try to make the best of a situation that you have. We actually have 2 upper-level courses that are all about, they spend a whole semester on how to find maxes or mins of certain kinds of functions. 418 for linear functions, and 419 for nonlinear. I taught 419 once. These are not always offered. Maybe they're offered every couple of years or something like that. But something to keep in mind because it might be among the more interesting electives that you could find just because of the obvious real-world application. Okay, so if a procedure from before of finding maximum doesn't work, would not work this time, what do we do instead? Oh, it's nice that the tables are pushed back. I feel like I have more room up here now. Okay. Okay. So instead of solving this equation, the gradient of f being equal to the 0 vector, what you do is you solve this equation that the gradient of f must be equal to some constant times the gradient of your first constraint, so lambda 1 times gradient of g1 plus constant times gradient of g2 and so forth. So however many constraints you have a term for each one. Okay. And these constants, lambda 1, lambda 2, up to lambda m, those are new independent variables. So you have your x1, x2, xn from before as independent variables. Now you have even more. So these new independent variables are called Lagrange multipliers. So that's where the term gets its name. This approach to solving this problem is called the method of Lagrange multipliers. So the idea is by throwing in more variables, we can have a system of equations to solve that, although it's going to be more difficult because of the extra variables, still we can actually find a solution, like a max or min of f that actually obeys all of these constraints. Now, I should mention I can actually relate this to what we were seeing before, when you didn't have any constraints. So solving this is equivalent to finding regular critical points. In other words, the same kind of critical points as last time of this function that I'll call the Lagrangian, which is, I'll call it h, which is a function of all the variables that we have, your x's, and also your Lagrange multipliers. So we have n plus m variables in total. And the formula for this function is just the function you're trying to find a max or min of, f, and then you just subtract off each Lagrange multiplier times your constraint function. So lambda 1 g1 plus lambda 2 g2 up to lambda m gm. Because if you were to take, wait, that should be at lambda 2. If you were to take the gradient of this function, and by that I mean differentiating with respect to all the variables, your x's and your lambdas, and set that equal to 0, you would get exactly this. Okay. And the thing is, the only way that the gradient of this can be 0 is if all the constraints are satisfied, because so the gradient of h, well, first you have a gradient with respect to the x variables, so that would just be gradient of f minus lambda 1 gradient of g1 and so forth up to lambda m gradient of gm. So it's exactly this being set equal to 0, because we want this whole thing to be 0. And then if you take the partial derivative of this with respect to any of the lambdas, well, this part would be 0, because this doesn't have any lambdas in it. And then the derivative of each of these with respect to one of the lambdas would be g1, g2, up to gm, because these are just linear functions of the lambdas. So the only way the gradient of this whole gradient can be 0 is if this is satisfied, and all of these g's must be equal to 0. But those are the constraints that we had at the outset. So, so you could think of it either way. Now we're trying to solve this equation subject to the constraints. So those still have to be enforced. Or you can think of it as, okay, now we have a function of more variables, your x's and your lambdas, and we treat that as a regular max-min problem and set its gradient equal to 0. All right, so let's take a look at some examples of how we solve this kind of problem. So the actual calculus part, there's not much to that. I mean, I've given you the equation you need to solve, but how easy or hard that is to solve, that just depends on the function. So you're going to have some nasty algebra ahead of you that's highly problem dependent, as we'll see. Okay. So for our first example, we want to find the any maxes or mins of this function, f of xy is 4x squared plus 9y squared. Subject to this constraint, x squared plus y squared minus 2x minus 2y minus 2 is equal to 0. All right. Now, to try to visualize what it is we're trying to solve here, I'm going to graph the function f as defines a surface. Now, because it's the x squared and y squared have different coefficients, the level curves of a surface are actually going to be ellipses. So we start out at 0, 0, and so I'll draw a few, okay, x, y, z. So, okay. Okay. So something like this. So if we didn't care about the constraints, the minimum value would clearly be 0, because you can't get anything negative out of that. If you set x and y equals 0, you're going to get 0. Clearly there's also no maximum, because the function f is going to go off to infinity. But that's when there's no constraint. Here we have this constraint to satisfy. So we're only going to be considering certain x and y that satisfy this. Now, can anyone tell me what kind of equation is described? What kind of curve is described by this equation? Anyone take a shot at it? We've seen this sort of thing before. I know it's Friday, but more specifically. So it's not wrong, but yeah, it's a circle. Yeah, if the coefficients of x squared and y squared had been different, it would have been an ellipse. So in fact, you can complete the square, but x squared minus 2x, and I'm going to add in a 1, and add a 1 to the other side, and then y squared minus 2y, oops, I need to add to both sides, y squared minus 2y plus 1, so I'll add a 1 to the other side. And then I have minus 2 is equal to 2. So this condenses to x minus 1 squared. This condenses to y minus 1 squared. I'm going to take this minus 2 and move it to the other side. And we get 4. So the equation can be written in this form. So what we have is a circle. And the center is at 1, 1. And the radius is 2. So if we were to identify those points in the xy plane, we have this circle, so we're only considering these x and y, and if I were to project that circle onto this surface, we're really looking for the max and min of this function, f of xy, only for xy on this circle. Okay. Now, in some cases, if a constraint is fairly simple, it may be possible to, for instance, solve for x in terms of y, or vice versa, and then substitute that in here. And then you reduce the problem of finding a max or min of a function of 2 variables to a single variable max or min problem. But in a case like this, and most other cases, you can't count on being able to do that. So that's why we have this procedure of Lagrange multipliers. So this right here is my function g of xy. So I only have this one constraint. So in my previous discussion, m is just equal to 1. So how are we going to use the procedure of Lagrange multipliers on this? We need the gradients of f and g. And since we only have one constraint, we're only going to have one Lagrange multiplier. So at least we're only adding one variable to the mix. Okay. So we're going to solve this equation. Gradient of f is equal to lambda, or 1 and only Lagrange multiplier, times the gradient of g. So to set up these equations, all right, so what is the gradient of f? Or its partial derivatives with respect to x and y?
8x.
Mm-hmm.
And 18y.
Okay, all right. And then we need the gradient of g, so its partial derivatives with respect to x and y.
2x minus 2.
Mm-hmm.
And 2y minus 2.
Yeah, okay, so these are functions have a relatively simple form. So now we need to set up our system of equations. And we don't forget, the constraint still applies. So you will always have a system of equations to solve, and the number of equations is going to be how many independent variables you have, so 2 in this case, plus the number of constraints. So we're going to have a total of 3 equations to solve. So we have df dx is equal to lambda dg dx, df dy is equal to lambda dg dy, and then g of xy, the constraint must be equal to 0. So this is good to keep in mind in general for these kind of problems, that if you have one constraint, this is what your system is going to look like. If you have more than one constraint, you would have additional terms, like I'd have lambda 1 g1x plus lambda 2 g2x, and you'd have more constraint equations down here. So in this case, with this particular f and g, we're going to have, okay, fx is equal to 8x, and then we have lambda 2x minus 2, and then we have 18y is equal to lambda 2y minus 2, And then we must have x minus 1 squared plus y minus 1 squared is equal to 4. So all three of these equations have to be enforced. All right. Now, and we have three variables that we're solving for, x, y, and lambda. Now, lambda itself is not as important because ultimately we want to find here are some points x, y where a maximum occurs. But if actually solving for lambda is necessary to get that, then of course we want to do that. Okay. So, now, of course I have this worked out on my notes, but what do you think might be a good idea to try, especially if it can help to eliminate a variable?
You set x equal to 0 or y equal to 0.
Simply setting equal to something, unless you have a concrete reason for it, generally is not going to help. Now, one way to eliminate lambda is if I could take this equation and rearrange it for lambda. We have lambda is equal to 8x over 2x minus 2, which can be simplified. You can divide both top and bottom by 2, 4x over x minus 1. But you can also do the same thing over here. What's another expression for lambda? Yeah, and then you can divide top and bottom by 2 there, so you get 9y over y minus 1. And since you have both these expressions equal to lambda, you could set them equal to each other. Okay. All right. Now, and of course we have x minus 1 and y minus 1 elsewhere in our equations. We have both of those expressions here. Because if you can get to a point where you can eliminate either x or y, then certainly that would help a great deal. But, like for instance, on the other hand, if you were to do that, we wouldn't want to do this in a way that introduces troublesome square roots, because that's something that would definitely complicate the algebra. For instance, I could see squaring both sides. And then what you could do is you could take either x minus 1 squared or y minus 1 squared and use this equation to eliminate one of those two. The trouble is, let's say if you go ahead and eliminate y minus 1 squared. So this would be the same as 4 minus x minus 1 squared. The trouble is you still have a y in there. If you would eliminate x or y entirely and have one equation to solve for the other variable, that would be great. So what I'm going to do now is I'm going to back up and try a different approach, and one that's actually in my notes. But I decided to go down this path anyway to show you that sometimes that happens on a problem like this, where it's not like some other equations, like quadratic equations, where it's clear that you know what to do. Sometimes you're going down the wrong path. You need to back up and see if something else might work. So maybe eliminating lambda might not have been best idea. Now, what you could do instead is we go back up here to our original equations. Here I took this equation and solved it for lambda in terms of x. We could go the other way. We could solve for x in terms of lambda. So if I have 8x is equal to lambda 2x minus 2, let's write it down here. And I'm going to divide through by 2. So I could solve this equation by rearranging for x. So I'd have, if I multiply it out, I have 4x is equal to lambda x minus lambda. But now I want to isolate x. What would that give us?
Isolate lambda at this point?
No, isolate x. Yeah.
So we should just subtract lambda x and move it to the other side with the 4x and then factor out the 4x. I mean, just the x.
Yeah, if you will, you can move this to the other side. Have anything with x on one side. Yeah, and then factor out an x. Something I know you should all be able to do. I know.
So x is going to equal minus lambda over 4 minus lambda?
Yeah. Or get rid of minuses. So also lambda over lambda minus 4. All right. Okay. And then you can do the same thing with this equation. We also have 9y equals lambda times y minus 1. And you can use the exact same approach. And since I saw so many pained looks among you from the last time, and whereas if more of you had gotten involved, maybe you could have moved things along a little better. Okay, so same thing as different numbers, so lambda over lambda minus 9. And so now, since you have an expression for x and an expression for y, and that came from these two equations, then you can use the only equation that we haven't made use of yet, this one, to try to make some headway on solving for lambda. So now you can take this and substitute it in for x. You can take this and substitute it in for y. Because now you've reached your goal. Your goal is to get some equation that only involves one of the variables. Doesn't matter which one, x, y, lambda. In this case, lambda. So if you substitute this in here and multiply everything out, which admittedly is an algebraically gross exercise, what you get is this equation. 4 lambda to the 4th minus 104 lambda cubed. 7 lambda squared. Something you'd want to have one of those fancy calculators on hand to solve. Okay. Because we had a quadratic equation, but then we have these fractions that we're substituting in. So after multiplying out and getting rid of denominators and so forth by multiplying through, this is the equation that falls out of it. Now, this is sort of equation that one would not expect to be able to solve by hand. certain calculators can do it. And since it's fourth degree, there are 4 roots altogether, but 2 of them are complex, so we're not going to think about those. The only real roots that you get, so lambda 1 would be 3/2, and also, that's the decimal, roughly 13.6. And so then what you can do is, once you have values of lambda, you can substitute those back into these equations to get your x and y. And now, so now you have 2 points to consider. You can think of as critical points. So substituting lambda equal to 3/2 in these 2 equations gives us, so x and y turns out to be minus 3/5 minus 1/5. And substituting this value of lambda into these equations gives us xy is roughly 1.42, just the 2 decimal places, and 2.96. Okay. Then what you would do, the very last thing is, now that you have critical points, you don't know which one of these are max or min, subject to the constraints. So you can take these points and substitute them back into f. So minus 3/5 minus 1/5 gives us a value of 9/5. And then plugging the other one in, 1.42, 2.96 is roughly 86.675. So what's happening is we took this circle and we basically, if you were to evaluate fxy on all xy in the circle, what you would find is this is where the minimum occurs, and right here is where the maximum occurs. Okay, and that's it. So, set your gradient equal to this Lagrange multiplier, new variable lambda times the gradient of g. In the case of one constraint, you must enforce your constraint. That has to be satisfied too. So with all the equations in front of you, you can see from those, it's not always clear, unfortunately, which is the right, easiest way to go algebraically. Again, that's something that's very problem dependent. Any questions about this one? Don't worry, I put such a problem on test 2. And I'm most interested in whether you know the general method of Lagrange multipliers. Do you set up the right equations? And if you do, then of course I want something that could be solved in a reasonable amount of time. And I say if I put it on the test, because by then you'll also be doing double and triple integrals, and you need to do those on the test too. Okay. Now, for a second example, we'll show one that has, here we had only one constraint. Here we're going to have 2. And sometimes the function, your objective function, that you want to maximize or minimize can be a very simple one. It's just that the constraints make things difficult. So we want to find the maximum or minimum of this function, and that function just describes a plane in 3-dimensional space. So normally, it would not have a max or min. And our constraints x squared plus y squared equals 1. Now, you might think, oh, unit circle. But keep in mind, we're in 3-dimensional space. Our function depends on 3 variables. So this equation describes in free space not a circle, but not a sphere, because there's no z. Really, z can be anything. So if you take a circle, but then you throughout all 3 space. So like let's Z run from minus infinity to infinity. It's a cylinder. Where the center of the cylinder is just the entire z-axis and the radius is 1. And in the next chapter, we'll be dealing with cylindrical coordinates, so it's important to keep this in mind. So equations involving like x squared plus y squared plus z squared, that's a sphere. If you only have 2 of the variables, but you're in 3-dimensional space, it's a cylinder. And then that's one constraint. So this is our G1. Actually, I'm going to write this as something equal to 0. So this is G1 of x, y, z. It just happens to not have a z in it. And our second constraint, G2 of x, y, z, is 2x plus z is equal to 1. All right. Actually, I'm going to need to write this way. Minus 1 is equal to 0. So what kind of geometric entity would that kind of equation describe? It's something we would have seen in Cal 3. It's a plane. This is the equation of a plane. Okay. So we're trying to find the maximum of this function subject to, so we have this cylinder. That's centered on the z-axis. But then we have a plane, this, and it's not meant to be an accurate graph of the plane. So this plane is cutting through the cylinder, and we have this intersection here. So that curve, like this oval-like curve, describes a set of all x, y, z that we could possibly consider. And since this is our function, x plus y plus z, we want to find out the max or min of the sum of all of these coordinates. Okay. So when we set up a method of Lagrange multipliers, since we have 2 constraints, we want the gradient of f to equal to lambda 1 gradient of g1 plus lambda 2 gradient of g2. So we have 2 Lagrange multipliers. So we need to line up our gradients. So we need fx, fy, fz. So what would our gradient be? What's all the partial derivatives of our f?
1, 1, 1.
Yeah, so at least that part is simple. And then we need the gradients of g1. So derivatives of this function with respect to x, y, and z.
2x, 2y,
And 0, because there's no z. And then gradient of g2.
2, 0, 1.
Yeah, 2, 0, 1. Okay, so now we can set up our equations. Now we have 3 independent variables, x, y, and z, and 2 constraints. That means a grand total of 5 equations. So we have fx is equal to lambda 1 g1x plus lambda 2 g2x. And then fy, same thing. So this is what the equations would look like in general for 2 constraints. Whoops, that's, my parentheses were bad. g2x, g2y, then lambda 1 g1z plus lambda 2 g2z. And then we have our 2 constraints. So x squared plus y squared equals 1. 2x plus z equals 1. This last equation is pretty convenient because that gives you an easy way to eliminate either x or z in favor of the other. So if we now fill in the particulars, so fx, fy, fz, well those are 1, 1, 1. And then g1 with respect to x is 2x, so we have 2x lambda 1. And then g2 with respect to x is 2, so we have 2 lambda 2. Then, for the second equation, g1 with respect to y is 2y, so 2y lambda 1. And then g2 with respect to y is 0, so that's nice. We don't get anything else there. And finally, g1 with respect to z, we get nothing. And then we have just a 1 here. So we just have lambda 2. All right. So finally, our constraints, x squared plus y squared is equal to 1. And so we have 5 things equal to 1. This is kind of how it worked out. But the nice thing is, lambda 2 is solved for. It's equal to 1. So I can just go ahead and get rid of that. So we only have 2 here. And certainly I can, well, actually we can simplify this even more. So since lambda 2 is equal to 1, I can say 2x lambda 1 is equal to minus 1. So this equation has been accounted for. Okay. Now, if we compare that equation, so the simplified first equation to the second one, I have 2y lambda 1 is equal to 1. Can anyone tell me, by looking at just these two equations, how do x and y relate to one another? In fact, you could solve each of these for x and y.
X is negative y.
Yeah, x is equal to minus y, because from these you can get x is equal to minus 1 over 2 lambda 1, and y is equal to 1 over 2 lambda 1. But those are negatives of each other, so x is equal to minus y. So that helps a great deal. Because now we can substitute that into this equation that has only x and y in it. So we've already made use of many of our equations. Oh, totally forgot to. All right. Well, while I'm erasing, I will leave that up there. Sorry for the several people who have to watch this, except maybe we should have been in class. Oh, speaking of which, let's find out who they are. Almost there. Okay. So from x equals minus y, and we also have the equation x squared plus y squared is equal to 1. So I can substitute in here 2x squared is equal to 1. Because you square a minus y and you get y. You get positive y squared. So x must be what? Anybody?
Plus or minus
Not 0.5.
square root.
Yeah, plus or minus 1 over square root of 2, or square root of 2 over 2, but I no longer have my 7th grade teacher yelling at me to rationalize, so I'm not going to. Well, she always insisted we say not minus 1, we say negative 1 and stuff like that. When I get to college, my calculus professor is saying minus 1. It's like, oh, it's okay. Okay, so now we have values for x, and therefore y is just a negative that. I'll write it this way, minus plus 1 over square root of 2. And we know how to get z because 2x plus z is equal to 1. So I can just go ahead and substitute these values in for x. So so now we have our two critical points. X2, Y2, Z2. Okay, so the first one, we choose a plus sign, 1 over square root of 2, minus 1 over square root of 2, and then plug that into Z, and we get 1 minus the square root of 2, and then negate the x and y, and then we have 1 plus square root of 2. So we've now made use of all 5 equations. And then if we plug these in to our original function f, we just add these up. Well, the x and y will cancel. So we have 1 minus the square root of 2 and 1 plus the square root of 2. So this one is a minimum on that set, that oval that satisfies the constraints, and this one is the maximum. All right. So any questions about the algebra for that one? You can write down Timber's name since I know she was here. Okay. Well, we've come to the end of our time anyway, just about. So what we have for Monday and Wednesday, well, of course we have to do review for the test. We can also use that time to cover the gist of the section right here. But then it'll also be a free-for-all in terms of any ongoing homework problems. So basically, whatever helps boost your grade is what we'll do. Okay, so be sure to bring your questions on homework, since clearly we'll have time for that. And again, be sure to get to the practice test soon. I will go over it. As time permits, not only doing the problems on the test, but if I think of variations on the spot, I can do those too. Just so you have an idea of what sort of problems can appear. Okay. Make sure you sign the attendance sheet if you haven't completed it yet. Oh, okay. I'd like to get that.